Huge problems require out-of-this-world solutions. James from Planet is here to share how they are pushing the boundaries of geospatial tech towards a more sustainable environment. James, please.
Good morning, everyone. I'm very excited to be giving this presentation today, and I'll start by thanking Switch and Hello Tamara for inviting me for this talk. I only wish it could be in person rather than virtual. My name is James Mason, and I'm the Senior Vice President of Space Systems at a company called Planet. We're a geospatial data company that also builds and launches satellites. And today I'll be talking about the work we're doing to advance sustainability from space. So we've been lucky as a civilization to live in a period of relative calm and prosperity for the last 70 years or so. We're now 20 years into the 21st century, and we're facing some unique and very complex challenges as a global community. The population is growing, and with it, our need for food and energy and raw materials and living space is straining the carrying capacity of the planet. Global temperatures are warming, sea levels are rising, and the weather patterns and disasters are seemingly becoming more extreme every year. Record high temperatures have made the 2020 fire season the worst on record in both the northern and southern hemispheres. This November in Australia, more than 80% of the Blue Mountains World Heritage Area was lost to massive wildfires. Similarly, in California this summer, wildfires burned more than 4% of the state, an area about 25 times the size of Singapore. This destroyed towns, led to extended power cuts in Silicon Valley, where I live, and polluted the air to the point where we literally couldn't leave our houses for a few days. It's estimated that 91 million tons of carbon dioxide was released into the atmosphere from California alone in 2020, and that's an amount equivalent to the annual emissions of about 20 million cars. In July of this year, the last intact ice shelf in the Canadian Arctic, the Milne Ice Shelf, collapsed, sending large ice islands out into the Arctic Ocean. In short, the environment is in crisis and experiencing unprecedented rates of change that are already having a significant impact on the lives of people around the world, as well as costing the economy trillions of dollars. As cities grow and forests are replaced with farms, the destruction of natural habitats means we're also in the midst of a biodiversity crisis. Wild animal populations have dropped more than 80%. Almost half of the world's coral reefs are already destroyed. And it's estimated that we're losing something like 150 to 200 species every day to extinction. And it's truly not an exaggeration to say that we're in the middle of a mass extinction event, the sixth one. We are also in a very dynamic and evolving geopolitical landscape as countries face new challenges from all these climate change issues, resource pressures, and populations that are either growing rapidly or aging or just generally restless. Additionally, the global superpower balance of the last 30 years is shifting as China and Russia become more bold and assertive on the world stage. Last and certainly not least, we are in the middle of a global pandemic that has stressed communities and economies and is raising serious questions about how fragile our supply chains and our public health systems are when they're faced with the unexpected. This picture here was taken by one of our satellites on the 28th of January, just days after the lockdown was imposed in Wuhan. And if you look closely, you can see that the streets are deserted and empty, and all economic activity had simply ground to a halt in a couple of days. Now, these are obviously incredibly complex and truly planetary scale problems, and we won't be able to fix them without first being able to see them and understand them. Without clear, objective data about what's going on, we will lack insight. Without insights and without the understanding about these really complex issues and the underlying causes and effects, we will be unable to take action. Or even worse, if we take action, we will make uninformed decisions, and we won't understand the consequences of those actions until much later. So whether you're a scientist studying climate change, or a government economist setting policy, or a business owner assessing supply chain resiliency, at the end of the day, you need good data, you need accurate data, you need the data at the right time, and you need it at the end of the day to make informed and timely decisions. So for these types of truly global scale problems, remote sensing with imaging satellites, so taking pictures with imaging satellites, is an excellent tool. They orbit the whole Earth. They can take pictures of any country, and in a way, they provide us with a kind of mirror to study ourselves and to look back at ourselves and study ourselves and our planet and the interaction between ourselves and our environment. However, the traditional remote sensing approaches were not sufficient. Organizations, whether they were governments or businesses, often didn't have the information they need, the information I was just talking about. They might not have had imagery that covers the areas of the world that they care about, or they didn't have it at the right frequency or on the right day or the right time. Or maybe that data is just too difficult to access and use. It requires too many special skill sets or special software and hardware to actually use. And finally, even when they could get that data, too often it was very difficult to extract meaning out of the data itself and find the signal in amongst the noise of all of this data. The good news is that there's been some major trends in the geospatial and satellite industries over the last 10 years, which have really changed just about everything. First, agile aerospace came about. So this is a new engineering methodology that emphasizes continuous improvements in satellite development, and companies implementing this have radically lowered costs and shortened spacecraft development schedules. Secondly, data that was previously only available to governments really was made much more widely available, essentially today to anyone on the internet with a credit card. Thirdly, the rise of the really large internet cloud platforms like Amazon's AWS and Microsoft's Azure and Google's GCP, and all of the big data analysis tools that came with them have made it easier than ever to access huge amounts of geospatial data, to process global scale data sets, and at the end of the day, to just integrate them into your workflows, whatever you're doing. So in other words, the barrier to entry to being able to understand what's happening on the surface of the Earth has lowered dramatically, and it's really never been lower than it is today. So 10 years ago, back in 2010, a few of us who were working at NASA noticed these emerging technology trends, those three trends I just spoke about, and also realized that in order to transform into a more sustainable society, we would have to address the fact that there was a severe gap in high frequency global data about what was happening on the surface of the Earth. And so Planet Labs, now called Planet, was formed in a small garage in Silicon Valley, very typical Silicon Valley story, with a simple but very ambitious mission. So our mission was to image the whole world every day and make change visible, accessible, and actionable. So we set about designing and launching satellites over our first few years to start collecting this data, and then building software to operate large constellations and automate the operations of the constellations. And then finally making software to make this data accessible to those who at the end of the day need it. So scientists, government officials, businesses, humanitarian causes, news organizations, and much more. Today, we're over 500 people located around the world working together on this mission. Planet is a satellite company, but really at our core, we're a data company. Our goal remains to provide this geospatial data at the speed of change, at the speed of things changing on the surface of the Earth, so that people, organizations can make those informed, timely decisions that I was talking about. Our fleet today is over 150 satellites that are operating in orbit today. They fall into two different classes. The Planiscope Dove satellites are about 5 kilograms each, really small, and they fly in a large constellation to map the Earth's landmass every day at about 4 or 5 meters per pixel resolution. We also have 21 SkySats, and we have those in orbit, and they're able to responsibly task points around the world multiple times per day. Each of those satellites is about 100 kilograms, so roughly the size of a dishwasher. And the combination of these different satellites with different sensors is really powerful. It allows us to detect a change, firstly, in this lower resolution product, covering the whole surface of the Earth. And then we can, once we've detected that change, we can enhance or zoom in and take a closer look with a follow-up observation with the high resolution satellites. Both satellites collect normal visual imagery, so red, green, and blue imagery, but they also collect imagery in other wavelengths. Both of them collect infrared imagery, which is particularly useful for measuring the health of plants. By combining these different wavelengths, you can actually measure, for example, the chlorophyll content in leaves, and it's a good indication of the health of a plant. So traditionally, Earth observation satellites are rather big and expensive, and they take a long time to build and to launch. By contrast, Planet satellites are much, much smaller. They're tiny satellites by contrast, and they're much lower cost. But we launch them in much larger quantities. And in this way, we were able to collect an incredibly large amount of data at a relatively low cost. The basic approach here is to take a single large expensive mission and break that into many smaller, cheaper satellites. And then we can operate those satellites as a single coordinated constellation that are taking coordinated observations. There are a few very important advantages to doing this. Firstly, if a rocket launch or a satellite fails, the mission is not entirely lost. Instead, you only lose a small fraction of overall capacity. So resiliency is really built in from the start into the mission architecture. Secondly, it provides flexibility to upgrade your system over time as you continuously replenishing satellites, and it provides opportunities to fix problems or to add new features to the satellites and upgrade them, similarly to how you might upgrade your cell phone every 2 years with the latest and greatest. To do this quickly and cost effectively, we're vertically integrated. So we design, we launch, we operate, and we serve the data all ourselves. We design and built and operated our ground stations too. I mentioned agile aerospace earlier. Planet pioneered this methodology in the early 2000s. And it involves adapting the iterative software agile development methodology to how we produce hardware. So in our case, what that meant was rapidly iterating the design of the Dove spacecraft 15 times over a course of 7 years, so 2 or 3 times per year, incrementally maturing it, adding new capabilities, expanding the data set that are produced with every design revision. A key part of this approach was leveraging trends in R&D spending in other industries. So for example, we use batteries that were developed for electric cars and processors and solid state drives that were developed for use in tablets and laptops. And by doing that, we can take advantage of billions of dollars that others are spending in R&D. And all we need to do is qualify those parts for space and roll them into our designs. So in order to build hundreds of satellites and cope with the frequent design revisions, we've built out an in-house lean manufacturing capability with an emphasis on automated testing, in-house environmental testing, so that's simulating the challenging issues of having electronics in space, and doing just-in-time production, where we're able to focus on streamlining bottlenecks and how we produce and test satellites, and produce satellites at a rate of up to 40 per week if necessary. So, you know, if we're building so many satellites and we're rapidly iterating on our design, our strategy also needs to include frequent launches. And we've launched many times, and we use launches to space both to test designs, test new iterations, test new components in space, but also to deploy operational constellations. And to date, we've launched more than 400 satellites on 29 successful rocket launches, including 4 launches just in the past 5 months. So it's been an extremely busy year for us. Back in 2017, we had our biggest launch ever. Here's a video of this launch. It was 88 satellites launched on an Indian rocket called a PSLV. And at this time, it was the largest cluster of satellites ever launched on one rocket. It was this launch that got us to our full constellation and meant we could eventually image all of the land on the planet every day. This is kind of what it looks like. So once in space, the Doves orbit the Earth with their cameras pointing down and turned on whenever they overland in sunlight. The Earth rotates underneath the satellites every 24 hours, which allows us to get a full scan of the planet every day. So with so many satellites in orbit, and we have a relatively small engineering team, our systems need to be highly scalable and automated. So when we got started, we couldn't buy these capabilities. No one was flying fleets of this size. And so we had to develop our own software. So we've developed mission control software to automate just about everything that the satellites do. And we've built and deployed almost 50 ground stations. I think it's 47 ground stations at 15 different sites around the world to operate our satellites and download all the data. The image on the top right shows 6 of our ground stations in Iceland. But at the end of the day, all this cool space stuff we do is just for the data and what it enables. And we deal with a lot of data. Each day we downlink about 1,000 times the satellites pass over ground stations and download. We download about 15 terabytes per day. And all of this is transferred into our Google Cloud processing, where we filter out bad or cloudy images, we locate where they are on the Earth very precisely, we calibrate them for scientific use, and finally we make them available through either a web browser or through programmatic APIs to customers and partners. At the start of 2018, when this video was made, we had about 800 images of almost every location on Earth. Today, it's well over 1,000. And these deep imagery stacks provide a kind of time machine, so you can go and explore how the world is moving and evolving every day. This archive of ours now contains more than 10 petabytes of imagery, which is really an unprecedented amount of information about what's happening on the surface of the Earth. And so much so that it's quite difficult to work with at scale. And so lately, we've been developing machine learning software to process all of this imagery, get it in a format where it's more ready to be used for analysis and decision making. For example, this global map of roads and buildings created from our imagery can be used to estimate population growth in areas where census data might be old or inaccurate. And this brings us back to the global problems that we face as a society and the transformations that we need to go through. The sustainability transformation is needed for us to learn to live within our means on this planet for the long term. This will require us to evolve our economic and legal systems to account for externalities like environmental degradation. It will also require us to complete a digital transformation that's well underway so our governments and businesses can operate more efficiently and sustainably. And fundamentally to these transformations is being able to extract actionable information from large data sets, including from satellites and other devices like cell phones and sensors and vehicles. Finally, with big data comes big power and big responsibility. It's critical that we use this technology and data to provide global transparency and hold bad actors accountable. If we're too busy fighting and undermining each other, then we will never be able to achieve these transformations. And that's why Planet works very closely with international think tanks and the media and nonprofits who are using our data to report on global events and geopolitics. And we operate in a lot of different industries and verticals, and we've got partners and customers in all of these verticals that are doing things related to these transformations and themes. In the sustainability area, we've got customers that are working in sustainable and regenerative agriculture, biodiversity tracking, water management, earth sciences, forestry management. For stability and transparency, we've got customers and partners that are working on maritime domain awareness or border security or strategic transparency or disaster response. And finally, with digital transformation, it's really a lot of governments and businesses focused on supply chains, precision agriculture, location-based technology and services. So if we focus a little bit further on sustainability, back in 2015, the UN established 17 Sustainable Development Goals, the SDGs, which were intended to be a blueprint on how to achieve a better and more sustainable future for all. Obviously, meeting these by the target date of 2030 will require a significant contribution commitment from governments around the world. And we're at Planet committed to making our data available and accessible to efforts aligned with these goals. And these technologies, the way we see it, these technologies help us to make the invisible visible and to fill in critical gaps in our understanding of our changing dynamic planet. So just to give a few more examples, starting with food security, high cadence data is critical to precision agriculture because it allows farmers and agronomists to manage their fields more effectively. This increases overall yields, it reduces how much fertilizer and water is used, and generally reduces the environmental toll on producing food. This video is an output of a new product that we have that's providing continuous time series of fields throughout the growing season. The imagery can also be used to effectively manage forest stocks. For example, this is high resolution SkySat imagery that was used to detect and track a beetle infestation that was killing trees in New Zealand. And global forests are habitats for many species, obviously, and they're also huge carbon sinks. They regulate the global weather patterns, and they provide food and building materials and income to many people around the world. However, as everyone knows, they're declining at record rates. Because of this, forestry management and tracking deforestation is very dear to our hearts of planet. This video shows 3 years of deforestation occurring in the Brazilian Amazon. And in fact, the original concept for imaging the Earth every day at this resolution 10 years ago was driven by this exact use case. We thought that if we could see it happening on a daily timescale, then perhaps we could enable governments and enforcement agencies to actually intervene and prevent it. And earlier this year, we were awarded a contract by the government of Norway to provide universal access to this kind of data, this imagery, for 64 countries around the tropics, particularly to support stopping deforestation of the tropical forests. And programs like this are fundamental to being able to fully account for the value of natural resources that countries have, such as forests, and also to creating the policies and regulations that will actually incentivize their protection over the long term. This is a really interesting study that was done recently by one of our education and research partners. In April, when the COVID shutdowns and lockdowns halted all activity in Italy, it resulted in a dramatic reduction of the number of boats in the waterways of Venice. So the researchers actually took imagery from before and after the lockdowns and used that, comparing that imagery, used that to estimate the amount of suspended sediments that were in the water that were being caused purely by human activity. So this kind of analysis helps us to understand the effect that human activity is having on the quality of the water in these locations. Another project we're very proud of is the Carroll Atlas. We're working with a number of partners around the world to help map and monitor the world's coral reefs globally. And these maps are used first locally on the ground to bring understanding to the people on the ground who are locally managing these areas. They're used regionally for designing and managing marine protected areas. And they're used nationally for setting of broad conservation targets and indicators. Staying with water, in this example, this is another interesting one. Dove and SkySat data was combined with radar imagery, with nighttime images, and data from the automatic identification system that ships carry on them to reveal widespread illegal fishing in the waters between the Koreas, Japan, and Russia. Using this data set, they actually found more than 900 vessels that were violating UN sanctions by fishing in North Korean waters in 2017. And projects like these are critical to understand human effects on the marine ecosystem and to identify areas that might be becoming overfished. Final example here, planet imagery and analytics, like the video I showed earlier, has been used also to track urban development and the migration of populations. So in this example, building development was tracked over a year in 3 provinces in China to understand how different provinces were growing over time. And as populations grow and weather and the climate becomes more erratic, people are being affected more and more by natural disasters. We're very active in disaster management as well. And I'll show a couple of examples of this. This first one from 2018 was the powerful earthquake. I think it was a 7-point-something magnitude, that struck the island of Sulawesi in Indonesia, triggering a tsunami. So it's a very cloudy region, which makes it quite difficult to image with satellites. But with global daily monitoring, we had clear imagery from before the tsunami, and we captured imagery through the clouds just a few days afterwards. We also right away tasked the SkySat satellite to the high-resolution satellite to take a closer look, and we got this picture just after the tsunami, which was provided to response teams to help them with recovery planning efforts. Of course, many disasters are in fact man-made, and while we may not be able to ultimately prevent all of them, we can certainly mitigate some of their negative consequences. In August this year, nearly 3,000 tons of ammonium nitrate exploded in the ports of Beirut, killed dozens and injured thousands. And we were activated by the International Disaster Charter to provide before and after imagery of the sites of that explosion. Also in August, the Japanese oil tanker MV Wakashio began to break up and spill 4,000 tons of oil on a reef near Mauritius. Now, this was a major environmental disaster for a country with a fragile coral reef ecosystem and limited resources to fight the spill. And Planet supported this effort with daily SkySat tasking that was provided to first responders on the scene. And unfortunately, we caught the breakup that did occur over a few days. And this list of examples goes on and on. The takeaway here is that we're building a deep archive of activity on the Earth's surface, and we're now moving from just being able to observe and react to being able to measure and act in real time. So, for example, being able to intervene in illegal logging or fishing while it's happening, and being able to get rescue crews on site quickly enough to actually help. Looking to the future, the promise of this big data set combined with machine learning and AI is that it will enable predictions to be made. And if we can actually make forecasts or predictions about where we're going to have issues in the future, it will further improve our efficiency and decision making across all areas and all sectors. So where's this all going ultimately? We're right now entering what I would call the fourth generation of remote sensing. This is characterized by the combination and fusion of data from multiple different satellites and ground sensors, and the shift from delivering pictures to simply delivering insights or indicators. So, just as an example, the combination of daily imagery from Planet with other data sets like radar and LiDAR will allow you to create an indicator for forest biomass. And now that indicator can be tracked over time rather than having to look at the images, and can be used for tracking, reporting, verification of regulations. And it doesn't require anyone to have knowledge about satellites or geospatial data. The combination of all of this data from different sensors in space with machine learning and artificial intelligence and data fusion is going to make knowledge and understanding about what's happening on the surface of the Earth as accessible as Google has made information on the internet. And we call this a planet a queryable Earth, and we believe that it will provide the tools needed to actually realize the sustainable future and achieve some of those UN Sustainable Development Goals. And with that, I'd like to say thank you and end just by posing this question: what would you do if you could see daily change every day on the Earth? Thank you.